Welcome to the third episode of Zero to Autonomous in FRC Java. This is part 1 of a 2-part video explaining how to use PID to complete the autoline task. In this episode, we'll be focusing on why we need PID and the proportional term. In the next video, we'll be covering the integral term and the derivative term. Let's start by continuing our discussion about the robot arm we created in the last video. During matches, when we're placing or grabbing game pieces, the arm needs to rotate to a certain angle to reach the game elements. But if you try to do this with a joystick, it's actually surprisingly hard. First, the robot is sometimes really far away that drivers don't get a clear view of where the arm is at. Second, the communication lag between the driver and the robot can make the arm not very responsive and frustrating to control. Third, it would take a long time to tweak the joystick until the arm gets to our desired angle. Fourth, after the arm reaches our desired angle, if we release the joystick, the arm may still slowly fall down again. Although the arm can be hard to manually control using joysticks, we can try to automate it in the code to let the program control the arm for us. This way, instead of constantly tweaking the joystick, we can simply press a button and program the robot to tweak the joysticks for us. For example, if we only need the arm to rotate to 4 fixed angles during a match, we could control the arm using 4 buttons. Every button would tell the arm to go to a different angle. And when we want the arm to move somewhere, we just need to press the corresponding button. In this video, we will be going through how to automate mechanisms to do that. However, it is really easy to make mistakes the first time automating a mechanism, and the robot arm might move in crazy ways, including smashing into the front or the back of the robot.
Don't kill anyone or anything.
For this reason, we will first practice automating a drivetrain where things are less likely to break. After we are done with that, we will then program the arm in the coming videos. Alright. Let's go back to the autoline problem with a KOP chassis. We will program 2 buttons on our joystick. The first one tells the robot to drive itself forward for exactly 10 feet. The second tells the robot to drive back to where it had started. These 2 desired positions, the 10 feet and 0 feet, are called set points. To go to 10 feet, in episode 1, we basically said, if we can have the robot drive at 5 feet per second, and if we let it drive for 2 seconds, it should stop at 10 feet. This method is called dead reckoning. In theory, this should work. However, there are outside disturbances such as air resistance, wear in the motor and gears, and small bumps on the road. These disturbances will more or less affect the robot's ending position. In the last video, we added a sensor called the encoder on the wheels to tell the robot where it is at. Then the robot could repeatedly decide if it is there, and whenever the robot arrives at the set point, it could then stop itself. This method is called bang-bang control. It solves the problem of disturbances since the robot knows to keep going until it gets there. However, even after the robot stops the motors, momentum will still continue to carry the robot forward. To solve this problem, we want the robot to gradually slow down as it is approaching the set point. Another popular algorithm, called PID, can account for slowing down when the robot is near the set point. PID can also stop really accurately on the set point, and it can complete the movement very fast as well. These are some of the reasons why PID is commonly used to automate robots in FRC. The letters P, I, and D are acronyms of the 3 parts that make up PID. They stand for proportional, integral, and derivative. We will go through what each part does and how to tune each part. First, let's talk about the proportional term. The gradual slowdown can be done using the P term in PID. From the encoder sensor on the wheels, the robot can know the distance between the set point and where the robot is at. And let's call this the error. We can then tell the robot to have less and less speed when we have less and less error. Mathematically, the speed we output will be proportional to the error. The equation is output equals Kp times error. When the robot gets closer to the set point, the error will be smaller, and the output speed will be smaller as well. By multiplying the error by a constant, we can specify how much speed to output given how much error. For example, if the constant is 0.5, we are saying we want the output speed to be half as big as the error. If we want the robot to go slowly, we can make Kp small to make the motor output small. And if we want it to go fast, we can make Kp bigger to allow more speed to be outputted, and thus making the robot go faster. Also, Kp can make up for the robot's different physical attributes, such as weight, gearbox ratios, and friction. For example, if the robot was driving on a carpet which has more friction, but you still want to get the same speed, you can do so by increasing the Kp value. Therefore, you shouldn't copy my Kp value because your value will be different from mine. But I will show you how you can tweak your constant until your robot performs a movement that you like. But before we start modifying the constant, let's take a look at how proportional control works on the robot and how to implement it in the code. We will write our code into the autonomous periodic function, and here is an animation of how the function interacts with the robot. On the left are the buttons, on the right are the motors and sensors. In the middle is our code that runs repeatedly every 0.02 seconds, but for now let's slow it down to see what it is doing. And let's assume for now that Kp equals 0.1. Every time the code runs, it does 4 things. First, it reads our buttons, which tell it to go to 10 feet. Next, it reads the sensor, which says we are currently at 0 feet. And from that, it can deduce that it has an error of 10 feet. Then, because we told it to use its formula to calculate the motor output, it multiplies the error by our constant Kp to calculate the speed that it should be at, which is 100%. Finally, it outputs that speed to the motors. The next time the code runs, the buttons still tell it to go to 10 feet. The sensors say it is now at 5 feet, which leaves an error of 5 feet. Then, the formula calculates the wanted speed to be 50%, and the robot outputs 50% to the motors. Note that Kp is a number that never changes when the code runs, but the sensor position, error, and output speed will change. The third time it runs, the buttons say go to 10 feet. The sensors say it is at 7.5 feet, which leaves an error of 2.5 feet. Then, the formula calculates the wanted speed to be 25%, and the robot outputs 25% to the motors. The fourth time it runs, the buttons say go to 10 feet. The sensor says it is at 10 feet, which leaves an error of 0 feet. Then, the formula would calculate the wanted speed to be 0%. And the robot would output 0% to the motors, stopping it right there. At least that is the theory. The main takeaway here is that the code is dynamically changing the motor output according to our equation. In the animation, the code only ran 4 times, adjusting the speed 4 times. But in reality, the robot would readjust its speed 50 times a second, and that would make it seem like a smooth motion to the human eye. Now let's write the code to do that. Today, we are using an AndyMark chassis that has 2 spark motors on each side. We also have a Gray Hill optical encoder installed on the left side of the drivetrain. Now let's set up the chassis in the code. Like before, we will be using the Time Skeleton Advanced template. First, create 4 spark motor controllers controlling the 4 chassis motors. Next, create a joystick called Joy1 on joystick port 0. Then, create an encoder object. We have plugged channel A into the Roboreal DIO port 0 and channel B into port 1. We will set the reverse direction to true for now, and the type is K4X. And just like in the last video, we can calculate the encoder constant. Then, in autonomous init, we will set the encoder to 0 by calling encoder.reset. Now to the PID algorithm. PID is already available from the WPI library and is also implemented in some motor controllers. But for this video, to get a better understanding of what's actually happening, we will write the PID code ourselves. In autonomous periodic, we will first read the joystick buttons. If button 1 is pressed, the driver wants to go to 10 feet. Button 2 goes to 0 feet. And we want the robot to remember this command even after the button is released. So we will store this desired position in a global variable called setPoint. Next, let's get the sensor position and convert it into feet. Then, find the error by subtracting the setPoint by the current position. Now, we can get the motor outputs using the equation. We will store Kp in the global constant variable. Finally, output the calculated speed to the motors. To more clearly see what the robot is doing, we can graph its position time graph to the shuffleboard by displaying the encoder value in robot periodic. Now that we're done with the code, we need to find the right value of Kp. To do that, we will try out some different values and see which one works best on the robot. But which value should we try first? 0.1, 10, 100, 1000? A good starting point for Kp is when the robot goes forward at a reasonable speed at first and gradually slows down to 0 speed when it gets to 10 feet. Any Kp value will produce 0 output when there's 0 error. But the reasonable speed at the start will be 50% or 100% and not 1000% or 0.001%. In our equation, in the beginning, the error variable will get a value of 10 for 10 feet. And at that moment, let's say we want the output to be 50%. With the given error and our desired output speed, we can solve for a value of Kp. This value is just a wild guess, but it's a good place to start. Let's enter this value into the code. Now the code is finished, but before it will work, let's look at one common mistake, which is installing the encoder in the wrong direction. We have just made this mistake, and let's see what that looks like. The robot drove forward, but PID didn't stop the system at the set point. In fact, it just kept going forward forever. Again, the problem here is that the encoder is installed the wrong way. When the robot goes forward, the encoder tells the robot it's going backwards. But PID doesn't know if the robot is going the right way. Instead, as the encoder value decreased, PID thinks there's more error, so we should go faster. And this situation gets in a loop. The more PID spins the motor, the more error there is, and thus PID wants to spin the motor even faster. The solution is to make sure both the motor outputs and the encoder readings are positive when the robot goes forward. In the code, we will fix this by changing the encoder reverse direction to false. Having PID going the wrong way can be really scary, especially if this was on a robot arm where it might break. In the future, it's a good idea to disable the robot if something doesn't look right. A shortcut way to do this is to press the Enter key on your computer, and the driver station software will disable the robot. If your code is still not working, here are some tips for debugging. First, make sure the PID code is running. You can print to the console when PID is running and verifying that it prints out. Next, make sure you don't have other functions somewhere else fighting to control the same motor at the same time. You can print to the console near other motor.setOutput commands. This way, you would know if anything else is interfering with the PID control. Then, in your PID function, print all the variables out. Go through them one by one and see when they start to be wrong. This way, you can know that your problem is somewhere there. When doing this, explaining your code to another person or a rubber duck may help. So now that the direction of PID is correct, let's see how the robot performs with a KP value of 0.05. To see more clearly what happened, we can draw the robot's motion on a graph. This is the same graph you have displayed on your shuffleboard. The gray line represents the set point, the blue line is the robot's position, and the yellow area is the motor output value. Time is graphed on the horizontal axis, distance is graphed on the vertical axis on the left, and the motor output percentage is graphed on the right vertical axis. As we can see, the robot slowed down, but it didn't quite get to 10 feet. It stopped at about 7 feet. To make the robot go further, we will increase the KP value. Let's try KP equals 20. Now the robot can get to 10 feet, but it went too far because it slowed down too late. But when it tried to come back, it came back too far as well. This formed the oscillating motion. The goal for the KP value is to have it drive the robot near 10 feet with minimal oscillation. In the demonstration, although the left and right motors had the same output, the robot slightly turned left. This is because we were operating the motors too violently and the wheels were slipping on the ground. Because the robot is not perfectly symmetrical, the slipping caused the robot to turn. This is not a worry since the wheels will not slip once we tune it correctly. And despite this turning, we can still learn that large KP values caused oscillations. Let's decrease KP to 10 and try again. We can see that there's still a little oscillation. Let's decrease KP again and try 0.5. And it works quite well. You can spend a lot more time tuning KP to get a slightly better result, but this value is good enough for now. Let's compare the robot's motion when KP equals 0.05, 0.5, 10, and 20. When KP is too small, the robot doesn't have enough motor output to complete the motion. When KP is too big, the robot may become violent and oscillate to different extents. Our goal is to find a value of KP that is somewhere in between those two, that gets the robot to the set point with minimum oscillation. Great! The general motion of the slowing down is achieved. However, The problem with only proportional control is that it could be inaccurate. As you have seen, the robot could still be a tiny bit away from our set point. In theory, if there's any error, proportional control should continue to adjust the robot's position. However, when the error is tiny, the generated output will be tiny, and it may not even be enough to overcome friction, therefore leaving the robot unmoved. If the motion that the mechanism is trying to achieve doesn't need to be extremely precise, we could stop here and get a decent result. However, if we do want it to be extremely precise, how can we fix this? In the next video, we will solve this problem by introducing the integral term and the derivative term in PID. Thank you for watching this episode of Zero to Autonomous in FRC Java. If you find this video helpful, your friends might too, so please like or subscribe and tell your friends about it. Again, all this code is available on GitHub, the link is in the description below. And if this code didn't work for you, or if you have any questions, please send me an email. Until next time, happy coding!